Got it. Alrighty, well, thanks Jessica for that introduction. Really excited here to share with you the work that I've done for my master's, which has been focused on spring precipitation deficits that impact stream flow in the upper Colorado River Basin during the Millennium Drought. First, I'd like to acknowledge my committee, both Jessica and Bart, thanks for being here, and my funding source from the National Science Foundation under the Sublimation of Snow project. All right, with that, let's get going. So I'll start with posing a mystery that's been brewing in the Colorado River. What's been driving the recent dramatic decrease in stream flow? And if you've been paying attention to a lot of different news outlets from across the country, it's been hard to miss something that's been focused on the Colorado River in particular. And it's really because this region has seen dramatic change rapidly, but many diverse stakeholders rely on this river for water, power, food, recreation, preservation, and millions have become reliant on it year over year to be there. And in recent decades, that hasn't necessarily been the case. But before I delve into this mystery any further, let's get some background on where the Colorado is and where its water originates. So the Colorado River is a basin that's a vital water resource region for the southwestern United States. It covers around 7 states and provides water for over 40 million people in that southwest region. And it's separated into 2 distinct regions, the upper basin and the lower basin. And for this analysis, we'll be focusing on the upper basin, which spans 5 of these states. And its outlet is defined at a USGS stream flow gauge site down here at Lee's Ferry, which is below Glen Canyon Dam and Lake Powell. And we focus on this area because the UCRB, or the Upper Colorado River Basin, accounts for around 90% of the stream flow for the whole Colorado River, as measured down here at Imperial Dam, so kind of covering the span of the river basin. And within that region, for this analysis, we'll be focusing on the headwater regions, where around 70 to 90% of this UCRB stream flow originates in the snow-dominated regions. So with this brief intro, let's go back to delve into this mystery a little bit more. So when we want to look at stream flow over the UCRB, we use a product called a naturalized stream flow, which is an estimate for UCRB stream flow from the US Bureau of Reclamation, that tries to estimate how much water would have flowed past this Lee's Ferry point were it not to have been controlled upstream. So we've observed a significant decrease in annual naturalized stream flow during the Millennium Drought period, which is a period going back to 2000 and on through the present. And that's relative to both the observational record going back to 1906 and a baseline period that we're using to reference against for this analysis between 1964 and 1999. And I'll go into a little bit more detail why that is later on. So additionally, recent decades have shown an increase in the interannual variability of stream flow in the Colorado River region, meaning that predictions have become a little trickier to get right. And that leaves a lot of people who are reliant on this water wondering how much they might actually get each year. And additionally, this recent drought, this Millennium Drought period, has also established the largest stream flow deficits that have been recorded in the observational record. So stream flow has been low and stayed low for quite some time. But over the same period, we've seen a stark rise in temperature and a drop in annual precipitation. And it's these 2 things that prior research has really focused on as the 2 main culprits. So when looking at this question of what's been driving the decrease in annual stream flow over the UCRB, there's been focus on temperature increase and precipitation change. But these findings can diverge on what carries more weight, and these results can be model dependent, meaning that the model that you use can actually influence the results that you might see at the end of the day. So we wanted to see if we could address these stream flow deficits using as many observations as we could. So let's move back to this mystery again, when we're trying to explain stream flow deficits in the UCRB during the Millennium Drought. And let's start with a question, which is essentially, what is the major source for stream flow in the UCRB? And if you remember back to my little introduction, we have around 70 to 90% of that stream flow originating in the snow-dominated high mountainous terrain. So maybe if we start looking at, has snow changed in its transition to stream flow? Has that changed during this period? So snow comes to play a really important role in streamflow prediction through measurements made on or around April 1st, a period generally are aligned with maximum snow water equivalent, or SWE, which is essentially the volume of water you would expect if you melted a certain volume of snow. So years with more snow, we would expect more streamflow, and the opposite would be true for years with less snow. And so over time, we can develop a relationship where we have a certain amount of snow and we might grow to expect a certain amount of stream flow. But during the Millennium drought, we've seen a change in that, where we've had less stream flow that's been measured downstream for each unit of snow water equivalent. So we have this interesting point here. We have this, change in stream flow that's been observed, and we see that we're getting less stream flow per unit SWE during the Millennium drought. But why might we be seeing that? Well, perhaps SWE or precipitation during the winter has remained similar or hasn't changed much, but precipitation in other seasons has. Maybe after April 1st, in that time when we're seeing a lot of that stream flow coming down. So here's where we can start to dive a little deeper, and we'll first, before we get into this seasonal precipitation change, let's try to understand how precipitation falls over the UCRB and throughout the year. So I'll be talking about precipitation over the UCRB with respect to a water year, which spans October to the following September, and it tries to align with the central pulse of precipitation falling in like the winter and spring. So over the UCRB, annually speaking, or over a water year, we see most of the precipitation falling in the high mountainous terrain throughout the basin. And it's cold enough in these regions for a lot of that to fall as snow, since our annual mean temperature is well below 0 degrees Celsius. But how does this precipitation distribute throughout the year? Well, the UCRB is not as extreme as we might see in like a Mediterranean climate, like in California. So the distribution isn't fully skewed where we see, the major bulk of our precipitation coming in the winter and then very little in the summer, for instance. So when we look at the fall period between October and December, we get around 22% of our total water year's precipitation that's distributed generally, equally around the basin. But as we move into winter, we do get the bulk of our precipitation, and especially in that high mountainous terrain. As we move into spring, it falls closely behind in its in the total that it contributes to the annual precipitation, and it mostly again falls in the mountains or in the northern reaches of the basin. And then when we move into summer, the lower lying areas within the basin and the southern portions of the UCRB start to get their fill. So while our precipitation falls primarily in the winter and spring, the input will behave quite differently as it translates into stream flow. As you might imagine, a big rainstorm that were to fall on this spring, patchy snow, relatively saturated ground would probably relate to a different stream flow signal if that same precipitation event were to fall on our dry ground up here in the fall. So we wanted to center on this spring period as particularly intriguing. And it's also this transition between this big water resource that we have in the snowpack and the summer season when a lot of that water is being used both downstream by people and in the mountains themselves by plants growing and transpiring. So with all that background, let's return to our original question that we started out with. So we have stream flow in the UCRB that's declining, and our snow is giving us less stream flow. So has precipitation after April 1 changed? But is there any real broader scale evidence for this before we can make a hypothesis? So spring precipitation in the Southwest region is not projected to remain static over the 21st century. And here I show a couple of idealized storm tracks that might play out during the spring period as storms come in from the Pacific. So there's evidence to suggest there's a northeastward shift that has occurred in the mid-latitudes, meaning that some of these storms might not hit the UCRB that may have hit it in the past. Additionally, research has highlighted a decrease in the number of frontal storm events that are coming in from the Pacific due to a shift towards the summer circulation pattern that normally doesn't have as many storms coming into the West Coast. And lastly, there's also signals in larger scale climate patterns that can impact precipitation in this region during spring. So these 3 points give us and can kind of hint to cue up our first hypothesis, which is during the Millennium Drought, the UCRB headwater basin saw a significant spring precipitation decline, and this accounts for a relative majority of the annual deficits. So as we know, a large majority of both streamflow and precipitation originates in these high mountains. So we want to address this hypothesis. We're going to focus on basins centered in this region. But we're going to select from a suite of basins that are deemed suitable for climatic analysis like this, meaning there's minimal human infrastructure or water diversions in these basins. So we selected from 26 basins within the USGS Hydroclimatic Data Network, which are suitable for long-term analysis. And we compared our Millennium Drought period to the baseline period that aligns with the continuous streamflow record within these basins. And that will come into play a bigger role when we look at streamflow changes in these basins later on. And then lastly, we wanted to separate these basins by elevation bands to see if their behavior or their response to precipitation change was the same throughout all elevations ranged. Now we're sitting here in Washington, or I don't know where everyone else is sitting, but I can see how this lower elevation band below 2,900 meters can be a little confusing. So as you know, in Washington, we might consider something around 2,000 meters to be high elevation. But we're in Colorado, where our mountains are consistently thousands of meters higher, and our snow lines are consistently higher as well. So I'll try to emphasize that while these are still high elevation locations, relative to the headwater regions of the UCRB, they're separated into these bands as such. So now how will we address this question of precipitation change throughout the year? So to look at this, we'll use a product called PRISM. Its acronym is spelled out up there, and it's a commonly used precipitation product that has monthly temporal resolution, and that's available to span both of our periods. And it's also driven by observations at stations and is used as input for a number of different models, as well as model validation for those. So while it is still technically a model, it has been found to be relatively reliable within this region. And these monthly estimates were then spatially averaged over each HCDN basin, so those ones on the right, and the UCRB as a whole, as shown on the left. But we also wanted to see how these results would evaluate against station observation. So we selected from 11 different meteorological stations distributed both throughout these basins and throughout the headwater regions to compare what those results would look like. So now how will we evaluate the significance of the change between periods? Well, we're going to harken back to some basic statistical analysis by evaluating the difference between these two periods using a statistical test called the student's t-test, which basically looks for a change in the mean between two sets of normally distributed data. So since we think that there has been a decrease, we're going to use a one-sided test, meaning that we are testing whether or not there was a decrease in precipitation between periods. So we're only looking in one direction. Now, to evaluate the significance of our test, we need to use a threshold, basically saying that the difference between means is large enough to give us confidence that the change isn't just due to random chance. So we decided on an alpha level of 0.05 or a 95% confidence level to test against, and we'll also show results for an alpha level of 0.1 or 90% confidence. And so when our test shows a value below our threshold, we can be confident that the decrease was significant. So with that, let's start to delve into some of these results. And we'll start by looking at the annual precipitation change throughout both the whole USCRB and the basins that we're looking at. So over the entire year, we see a significant decrease in precipitation over the basin between our baseline and Millennium Drought periods. And these were highlighted by the largest differences occurring where we would probably expect them to occur, where we get the most precipitation. in the headwater regions. And within our headwater basins, all showed a semblance of a decrease, but 17 showed a significant decrease at that 95% confidence level. And these were mostly centered on our low and middle elevation basins. So now when we move into the seasonal aspect to look at how these deficits were distributed over the year, we'll first look at fall, where we saw a minimal, non-significant change over the entire basin and minimal changes over only 3 of 26 of our basins at that 95% significance level. In winter, we also don't see a significant change over the entire basin, but again, we do see the largest changes occurring, the largest decreases occurring in the headwater regions. But again, this is the season where we see the most precipitation. So that might be something we might expect. But only 4 of these headwater basins showed a significant enough decrease to meet our lowest threshold. And I'll come into spring in a second, but looking at summer, the minimal change was observed over the entire basin, and none of our headwater regions showed a significant change. However, during spring, we see something a little more interesting, where over the entire basin, we see a significant decrease between the 2 periods, with the largest differences, again, occurring in those headwater regions. And all the basins showed, and again, similar to what we saw annually, all basins showed a decrease, with 15 of 26 showing a significant decrease. But how much do these spring precipitation changes account for the total deficit over the year? So when the deficits in spring, the deficits in spring account for a relative majority of the total deficits. And I show this here by looking at those 17 headwater basins that had significant annual decreases. And 16 of those spring precipitation changes or deficits made up between 30 and 50% of those deficits, meaning that the rest of the 3/4 of the year was making up the rest of that deficit. But in that one basin that did not have that relative majority, it was a basin that didn't actually show a significant change in spring precipitation. So from all this, we can see that there was indeed a significant decrease in spring precipitation during the Millennium drought over the UCRB, and this spring precipitation change accounted for a relative majority of annual deficits. So going back to this question of less stream flow per unit, we saw that if we have less precipitation during the following spring, we might actually expect this shift to occur, since we're taking those measurements on April 1, and if we're losing that precipitation later on, we might see this shift where we're getting less stream flow during that period. So with these findings, is our problem solved? Well, no, not quite. I'm only 18 minutes in. So we have to ask, the precipitation decrease that we see also matches the stream flow declines. Like, are those in the same order? So let's move back to this plot that I showed a little bit earlier. But now we have our basin total precipitation on the bottom year over year, and our stream flow on the top. And so we want to see if this drop in annual precipitation over the Millennium drought period is also enough to account for the deficits that we see in stream flow. So we can quickly try to first order address this question by considering the average runoff efficiency of the basin. And the runoff efficiency is basically the ratio of stream flow output to precipitation input. So when we take the average over time and we multiply it by our precipitation, we can get a somewhat general estimate for how much stream flow we might expect from our precipitation. So for the UCRB, an average runoff efficiency is around 15%, meaning that if we had 100 raindrops fall on the UCRB, 15 of those would be measurable downstream as stream flow. So when we take this mean value and multiply it by our annual precipitation, we can get an estimate for what annual stream flow might look like. But how does this compare to our actual stream flow record? And we see that it does an okay job, except during wetter years, like in the mid-80s, and the drier ones that we're seeing currently. But dry periods have also occurred in the 70s, 80s, and 90s. So what's different about this one? Well, these deficits seem to have been consistently larger during the Millennium drought compared to our baseline period. And when we compare the two, directly and we want to look at how much our precipitation would need to be further decreased to account for that streamflow deficit, it would have to be about roughly doubled. So similar to what we saw with snow, we're getting less streamflow resulting from each unit of precipitation during the Millennium drought as well. So now we saw that spring precipitation can partially explain why we get less streamflow per unit SWE during the Millennium drought. But do we see these spring precipitation decreases? But we have to ask if these spring precipitation decreases have other impacts as well. So how else can we lose water from the surface? So we have to think of another way that water can and I put lose in quotes because it's not really lost, but we can return water from the surface to the atmosphere through a process called evapotranspiration. So we need to look at how spring precipitation decreases might impact spring evapotranspiration. But let's first get a rudimentary understanding for what evapotranspiration is. So evapotranspiration, or ET for short, so I don't have to keep saying that, is the combined processes of transpiration from plants and evaporation from soils and water surfaces. And I note here that it can be energy or water limited. And what do I mean by that? Well, it can be water limited in the case of, let's say, one extreme where we have no water. So if you have no water, there's nothing to evaporate or transpire. So you won't have, your ET rate will be limited by the water that you have there, which is none. On the other hand, it can be energy limited because this transfer is, this phase transition between liquid water and water vapor is a very energetic process. So you need a lot of energy available in order to do that. And if you don't have any energy available, be it from the sun or other terrestrial energy sources, then that evaporation or transpiration will be limited in itself. And that's important when we want to start to consider how we can estimate ET. And essentially, we need to either look at observations or models. And observations for a long record, like we want in this case, are few and far between because these measurements would be taken, in very far different places. And remote sensing methods that are currently available were not available in like the 60s or 70s. So we kind of have to look at models, but ET is a very complex process that is driven largely by small scale impacts that are difficult to resolve. So we want to ask if we can simplify our question during spring when we want to look at ET. Well, if I bring us back to this representative spring photo, we can think of what the land surface might be like here. We have this patchy snow, we have pretty saturated ground. So it seems like our situation wouldn't be water limited, but we might be, or can be limited in this case, and can limit our ET is the energy that's available. And that's where this idea of potential evapotranspiration comes in, which is essentially the total amount of water that the atmosphere could suck up at any given time, given the amount of energy that you have. So it gives us an estimate of, the total energy available to evaporate or transpire water. And using easily measurable meteorological variables, we can get a reasonable estimate for what this PET would be. So we're going to reformulate this question to how can precipitation impact PET? Well, let's first imagine our watershed with less precipitation. And this lack of precipitation would also likely coincide with less cloud cover, meaning that we would expect greater net radiation into the surface since less of that, or more of that, or less of that is being reflected by a cloud layer, let's say. And we would also think that this would lead to higher temperatures. Hannah was saying earlier that when she stood out in the sun, things were quite warm down in Yosemite. And you could probably think that if you stand out on a sunny day, you'll probably feel quite a bit warmer than you would on a cloudy one or when it's raining. So this increase in energy available would also correspond to an increase in the potential evapotranspiration, or PET, that's available. Now, let's consider a situation with more precipitation and cloud cover. So we'll have less net radiation making it through to the surface. Oh, sorry, less solar radiation making it through to the surface, meaning that we'd have a total less net energy at the surface. Additionally, we would expect that if storms are rolling through, especially in this mountainous terrain, will have quite a bit cooler temperatures. And so these two combine to lower the energy that we have available to evaporate or transpire water. And this may make sense if you think of like when you want to water your garden or something. If you're out there on a rainy day or a cloudy one, the atmosphere isn't going to be asking for a lot of demand from the plants that you have. But if you're out there on a sunny day, then like yesterday, for instance, I did have to water my garden. So this screws up our second hypothesis that we want to test, where we look at years with less spring precipitation corresponds to years with greater PET. So let's get into how we'll evaluate this relationship. To address this hypothesis, we're going to narrow down our scope to a particular basin within our HCDN network, the East River Basin. And we chose this one because we can utilize or take advantage of a couple different data sets that were run over this particular basin. So our data for PET comes from first using a 1 kilometer weather research forecasting model run between 1987 and 2020 over the East River Basin. And we estimated potential evapotranspiration using a modified Penman-Monteith equation. I won't get into the nitty-gritty details, but essentially takes a number of different meteorological inputs and spits out a PET estimate. Additionally, we used 4 kilometer TerraClimate PET data, which is a data set of monthly climate and climatic variables over the global surface. And then lastly, we used a 4 kilometer prism temperature to estimate PET using an equation that's temperature index called the Thorthwaite equation. So how we matched these data sets is we wanted to match them to the time series that we had from the WRF model run. So we used data from 1987 to 2020 for all those 3 products. And precipitation, temperature, and PET were spatially averaged over the basin. And PET and precipitation were aggregated to their spring totals. So then we would compare spring precipitation totals against the spring PET and then the mean temperature over that spring. So to get an idea of how precipitation and spring PET would relate, let's look at 2 years over the East River Basin, a relatively wet one on top and a drier one on the bottom. And first, we'll look at what snow does. We'll look at a couple different water variables to just see how they respond to this year. So we have more snow in that wet year than we do in the dry one. We have monthly precipitation also showing a similar signal, especially in that spring period. We have much less precipitation. And as we would expect, streamflow would be much higher in the wetter year than in the drier one. But then when we look at PET in spring, we see that PET in that drier spring is around 20% less than what we saw in the wetter year. So now when we look at year over year between that 1987 and 2020 period, let's see how they evaluate against each other. So looking across our different products, we see that years with lower spring precipitation on the x-axis correspond to years with higher spring PET on the y-axis. And additionally, they generally correspond to warmer springs. And so to just repeat myself, getting back to this second hypothesis, we see that less spring precipitation corresponds to greater PET and warmer springs. So back to our journey to address this mystery. So to recap, we're trying to address what has been driving the decrease in annual stream flow during the Millennium Drought in the UCRB. And we observed that less stream flow for each unit SWE has been coming down during the Millennium Drought. And we generally explain this by decreases in spring precipitation that account for a majority of the annual deficits year over year. But we also see that we also saw that less stream flow per unit SWE per unit precipitation was coming down during the Millennium Drought, and that these precipitation declines couldn't fully explain that decrease. So we wanted to see how these might impact PET, especially during spring. And we found less spring precipitation corresponded to greater PET and warmer springs. So again, is our problem solved? Not quite. We have to ask if these impacts from our first 2 hypotheses would impact annual stream flow declines over all our basins equally. Like, would they be shared? Does every region show the same response? So how will we get into this? Well, let's first try to explain why they might not be the same. Well, here is where our basin separation by elevation begins to play its bigger role. So in the depths of winter, both our higher and lower elevations will have snow, but we can expect that our higher elevations would likely have a deeper snowpack. They have greater orographic influence on storms, and so you'll likely have a deeper snowpack there. So as we move into spring and temperatures warm, temperatures are going to be warming and rising above freezing first at these lower elevations, meaning that the snowmelt onset will be occurring earlier at these lower elevations. And that combines, since we also had that shallower snowpack, we'll expose the ground surface earlier, which will decrease the reflectivity of the surface or its albedo as we're transitioning from that white snow to the darker ground. And once that snow melts, our plants can start growing and transpiring. And as energy continues to increase with solar angles increasing over the year, we'll be getting more and more energy, and those plants, basically that life can start up a little earlier at these lower elevations. So we want to see if this decreased spring precipitation and this higher spring PET feedback that we saw is impacting stream flow in lower elevation basins more than in higher ones. So here we go back to our 26 HCDN basins, and we look at the stream flow gauges at the outlet of each. And again, we're going to be comparing our Millennium drought period to our baseline period. So we wanted to separate these basins again by elevation, as in the stream flow signal, they have quite different behavior in both their timing and stream flow kind of volume over the year. So as we normalize by the basin area, these higher elevations are showing basically more water coming out of them since they have more snow. And additionally, that timing question, we can look at a little bit here, where in green, I show the lower elevations and the cumulative distribution of annual stream flow over the year. So kind of how and when that stream flow is happening. And we can see that at those lower elevations, it's happening, or much of that stream flow, or the main pulse of that spring melt period, is happening quite a bit earlier than in those higher or middle elevation basins. And those middle locations are, somewhere in the middle. So similar to how we tested for significant changes in precipitation between our periods, we use statistical tests to evaluate the difference in stream flow volume between periods. And for this test, we used a non-parametric test, which doesn't require normally distributed data, since not all our data was indeed normally distributed. So again, we used a one-sided test where our null hypothesis was for no change in the mean, and our alternative hypothesis was for a decrease in stream flow volume between periods. So again, our test statistics were the same for evaluating that significance, with an alpha level of 0.05 or 95%, and we'll show the results for alpha is 0.1 as well. So let's get into what we saw. So over our entire basin, over the UCRB, we see that significant change in stream flow between our periods. And additionally, in all of our headwater basins, we saw some semblance of a decline between periods. But most of these declines were centered in the lower and middle elevation basins. And when we pull this up against what we saw in spring, we see a general similar signal, where we see those middle elevation basins, lower and middle elevation basins, seeing a similar response. So when we kind of plot these against each other, I can show a map of what the percent change in spring precipitation looks like, and that's the shading in this map, where blues are an increase between periods, reds are a decrease between periods, and the deeper the red is the stronger the decrease. Additionally, with the outlet stream flow gauges at each basin, where the shape of the symbol indicates the significance level of that change, and then the size of that symbol indicates the percent change between periods. So now let's take a representative to get kind of a better idea of what that looks like within a representative lower, middle, and higher elevation basin, to compare how they look more directly. And so our largest volume changes that have occurred between our periods were in our lowest elevation basins, corresponding to where we also saw those largest spring precipitation changes. And the timing has shifted earlier in all ranges, but the largest margins of those changes were in higher elevation basins. That wasn't a focus of this, but I can talk about that more later. So from this third hypothesis, we saw that low spring precipitation throughout was centered on those lower and middle elevation basins. And we saw that less spring precipitation corresponded to greater PET. And we wanted to see what that influence would be on those lowest elevation basins. And that's where we are also seeing these largest streamflow declines between periods. So where did this all lead us? And so I'll kind of go through where we started and where we have ended up. So we began by observing that less streamflow was occurring per unit SWE during the Millennium Drought. So we started by looking at precipitation changes in other seasons. And we found significant decreases in spring precipitation during the Millennium Drought. That was also accounting for the majority of any effects. But we wanted to see why for each unit of precipitation, we also weren't seeing we were seeing less streamflow. So we looked at how these spring precipitations might interact with PET. And we found less spring precipitation corresponded to greater spring PET and warmer springs. And so we wanted to see if the impacts from these first two hypotheses or these first two results affected streamflow in headwater basins differently, especially those separated by elevation. So we compared streamflow changes in different basins. And we found that streamflow declines were largest in our lower elevation basins. So when I draw back to kind of where we began, we began by looking at less precipitation over the UCRB during the Millennium Drought, and under a warming climate, we see temperature rising over the basin. But the impacts from these kind of combine and they interact with one another. There are resultant changes to cloud cover, evaporative demand that are more complicated than we necessarily addressed here. But these changes are also occurring most glaringly during the crucial spring season. And these deficits also appear to expand as we move towards these lower elevation zones in these headwater regions. But again, I say these impacts interact with each other. And I kind of show this by looking at the relationship between spring precipitation and spring temperature anomaly. And we see a relatively strong relationship where when we have a dry spring, we also have a warm spring. And this is stronger than the signal that we see in just spring temperature rise alone. So now that we've learned all this, what can someone like a water resource manager do with it? Well, again, spring temperature rise and precipitation decline both impact stream flow. And so we need to use spring precipitation as an important metric to include when we want to estimate how much stream flow we might have. And I just try to show this by looking at a linear regression with just SWE as a input variable. And we see, a relationship that exists, and it does an okay job. But once we add spring precipitation in there, we can really improve our model output if we just look at the variance explained for that single linear regression with SWE. Has a value of 0.44 and improves to 0.72 when we add spring precipitation in. But that isn't really necessarily anything new. As you add another variable in, these models will improve. But what is interesting is that there's been recent work focused on improving our spring precipitation forecast, and they can have insightful lead times up to a year. So if we can utilize that information, and along with the influence that spring precipitation has on this region, we can use that to our advantage. So lastly, where can we kind of go from here? Well, we have to ask what happens with continued warming. Will our higher elevation basins start to be impacted? Or will their deeper snowpacks continue to buffer them with time? But if we were to see winter precipitation decreases as well, and that snowpack in those high mountains couldn't build up as much, would we see the impacts on stream flow in those higher elevations more? And then another question is how does actual ET respond to these changes, especially in the saturated zone right around the rivers, that riparian area, and then drier areas that might not be saturated for as long? Do they all respond in the same way? And then lastly, we didn't address the important fluxes of soil moisture and groundwater that play an important role in streamflow generation within headwater basins. And that leaves another question of how spring precipitation deficits impact those as well. All right, so just to end things up, I just want to say a lot of thank yous. First and foremost, I want to thank my fiance, Grace. You've been an amazing support. I call you a network, but also just a single person that's been just super vital to me over the past number of years. And also our dog, Denali, the best companion of all. Also want to thank my family for just supporting me as I continue to pursue my passions here at UW. Want to thank the Mountain Hydrology Research Lab and the Treehouse Fishbowl grads. Y'all have been amazing mentors and helped me learn a lot, and it's been really fun, both interacting with you in the school environment and outside. Also want to highlight Eli Schwat. Living with you for a number of months was an awesome time. We got a lot of good memories, and I'm really happy we had that time. Also want to thank my advisor, Jessica. You've been an amazing mentor to me, and your help both on this project and giving me a lot of amazing opportunities. I just really thank you for that. And lastly, I want to thank the broader CE community. It's been an amazing time since coming in. I've really enjoyed my time and meeting a lot of new people, learning many new things, and just being in an area where, yeah, I can pursue work that I really love. So thank you.
Question from the audience.
Oh, thank you. Appreciate that. Yeah.
So when you include spring precipitation,
Mm-hmm. Right, and I think it's a point, like it's only one point on this plot, but that I find interesting is kind of this one on the far right, which was a year with pretty minimal April 1 SWE, and this is only looking at a single basin, so like this isn't a general idea, but this was a year where if we were just using April 1st SWE, we probably would have a pretty large residual. I think that's this point here, where we had, or actually where it is, but we had a little amount of April 1 SWE, but we had a pretty good amount of stream flow for the entire year. And that was also an extremely wet spring period. So yeah, it provides a decent amount of insight. And so kind of the point is that if we can improve those spring precipitation forecasts and really use that information to our advantage, then we can get kind of a better closure on where that, yeah, how that snow will translate into stream flow that we can use.
How much data is spring
I mean, I would say, like, if you were looking to choose a specific month that you really wanted to get right or something, if you and you had a choice between June, May, and April, I would probably highlight the April period, both because you still can kind of get that wintry influence where a lot of similar storms can still be coming in, and so if you don't have those or you do, that can really like change the dynamic of the start of the melt period. And then later on into June, that's one of the lower precipitation months for the year, because you're kind of in this transition period between a bunch of like convective storms and thunderstorms and stuff, plus like North American monsoon stuff going on later in the summer. And then you also kind of are far away from that winter influence. So I would kind of highlight the April period as particularly important. Yeah, so that's what I would say.
A lot of comments how excellent and clear of a presentation.
Thank you. Yeah.
Do you know if there's any like the low elevation or high elevation basin matter for water use?
Yeah, so in terms of water use, the lower Colorado River Basin is kind of where a lot of this water is being utilized, or it's being pulled out kind of like further downstream. There's less development in the upper basin, particularly things like the Central Arizona project. For instance, basically there's a lot of development in that lower region where if you're just pinpointing like water use in specific headwater basins, I don't think it necessarily matters as much. But then there's also a question of like what development will look like. I don't really know. But whether or not, these lower elevation regions will become more important for grazing or something. I don't know, but yes.
So I know you said you looked at like observation or regions where there wasn't development. So if you have like grazing or other development in this region, like did you look at research where like how that would impact your economy? Because like I feel like that's like very much like, oh, we're just going at this one subset where it's like a lot of those areas are seeing increasing recreation, whatever.
It's a good question. And we mostly focused on it because we don't essentially, because we want a continuous record of like nothing changing in these basins, or as little as possible. There will still be like grazing. For instance, in the East River, there is cattle grazing in that area. So there isn't like no human development, but it's more like, you know, in 1990, they didn't put in a dam, which would really influence like the stream flow signal that we would see. But it is important to and I guess that's kind of where why we utilize naturalized stream flow over the whole basin, because that's like an estimate of the total flow from the upper Colorado River, which would look very different from what is released by the U.S. Bureau of Reclamation from the dam, you know, which will have a cycle depending on power requirements and stuff like that. So like the reason is, you don't want to get influence from those sorts of changes that might really impact results that you get.
I just think like I get the point of the dams, but with the like I feel like people like building more vacation homes when
and I definitely think that in these areas there is some influence that I think is just really difficult to account for. But yeah, because like if you built a town that was like kind of a small town, but it would probably influence something going on there. And I don't know how much that would impact the signals that we're seeing.
Julie Vano has a question online. I can read it for you.
Cool.
She said, you allude to what water managers should do with this information. Does this also point to other things we should measure or other ways we should look at our measurements? For example, April 1st sweep, but would another measurement be better?
Yeah, like I think there has been some debate on whether or not April 1st sweep has remained the like be all end all best like estimate to use. But I've seen like both people saying, oh, we should move towards March 1st, or we should move towards May 1st. And I think it's more of a question of kind of seeing the interrelated impacts of things, where kind of using these singular estimates, we might have to start looking towards like more places, I guess. But yeah, I think that in terms of like specific measurements, I'm not sure how much. I mean, yeah, I guess more is often better, but not always. Doesn't always fix all our problems. It also depends on where you're measuring and how you're doing it. So it doesn't really fully address your question, but I guess there is like kind of discussion around this point of whether or not we really have enough to fully resolve changes that we're seeing. So yeah, I would say maybe to kind of fully address this, but yeah, I don't want to say if like, oh, we should change everything to measuring on May 1st or March 1st or something like that. But more of just considering more variables than just kind of what our winter snowpack look like. I think there are more implications than yeah, just what winter gave us. So a lot of current observational forecasts use antecedent soil moisture, so soil moisture from the previous fall, and that definitely has an influence and is important. And I started kind of this project by wanting to focus on soil moisture, but a lot of the estimates were just, it was difficult to actually kind of know what we're actually getting. Like if you put the soil moisture sensor out in the field, would it actually give you what, you know, this grid is telling you over a certain area? And I do think that it provides a lot of insight. But so I didn't look specifically at soil moisture kind of for this reason of we kind of wanted to focus on the main changes of like, okay, precipitation and stream flow. And then to address your question about fall precipitation, it also plays a role, not as I guess it has that influence on that soil moisture, which in turn will interact with how stream flow is generated in the spring period. But it does offer some insight, but not as strong as what we see in the spring, which would be nice because we could make those observations, use them, and then you're like, you don't have to worry about modeling as much. But I guess, yeah, if we always wish it was the easier option, but
That's follow. We don't see.
No, he's traveling. No, he's not. He's traveling. No big deal.
no, that's why we don't know.
Give Danny a day.
Thanks everybody online for joining.
Well, there, you can.